So today we do have an objective, and the objective is to understand how to solve area problems. And I really don't have a reference for you in the book, so today's notes is as good as it gets. But embedded in understanding how to solve area problems is a review of multiplying polynomials, which then has a review of exponent rules. So while the test you're going to be taking on Monday may not look like the quiz you took last week? I can't even remember. My brain hurts too much to remember what day we took something. What you're going to not see are those exact kind of questions, but you are going to see the rules are going to be in the questions we're solving, but they're just going to be more challenging problems that you're doing. You know, the scientific notation was a great way of showing the rules of multiplying and dividing with exponents. Also, we could make that with raising powers to powers. So, and in our word problems as well, they help out. And then when you were multiplying binomials and polynomials and so on and so forth. So it's not going to be you're going to have these individual little problems. You're going to have the bigger problems, but inside the bigger problems, you have to demonstrate that you know the rules. Okay? So the couple things to tell you about is because we're dealing with area, there's a couple of formulas that regardless of what kind of test you're taking, no one would ever give you these formulas because at this point you should already have these memorized. So the two particular area formulas that I expect that you know is the formula for the area of a rectangle and the formula for the area of a square. I will never give these on a test, and my expectation is that you know them. Sadly, many of you do not know them, and some of you confuse them with perimeter formulas. Okay, this is something that you should have been using since elementary school and have had several years of seeing them over and over again. So because these are formulas, these are equations, so equations have to have equals. So each one of these formulas start with A equals. Okay, for a rectangle, what am I going to do to get the area of a rectangle? Jason?
Multiply the length by the width.
So we just do length times width. Now I just want to draw a picture because I have this funny feeling that people don't quite get what area is. If you think back to the matrix and we were filling in the little boxes, we were telling you what was inside of those boxes. And that's really what area is doing, is asking for what's inside that rectangle. That's your area. Okay? Perimeter is what's the edge of that rectangle. All right, who knows the formula for the area of a square? I've got it started. A equals. Luke? Side to the, not to the fourth power, okay? Armand?
Side to the second row?
Yeah, it's just side squared. So S equals the length of one side. Since in a square all the sides are the same. And I had people first period were saying, oh, A equals L squared, A equals W squared. I mean, no, it's not. There is no length and width in a square because length and width give you the impression that they're different numbers. And in a square, they're all the same. Okay, because we're dealing with this notion of these different shapes, in order to see them, the diagram, drawing pictures is super important. So recommend highly, 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 and you're going to see me do it. And those of you who aren't doing it, I'm going to say shame, shame, shame. Draw a picture of the situation. Very important. That's really going to help you visualize where everything is, especially when it comes to coming up with all the dimensions. And because these shapes aren't dealing with a single rectangle or a single square, we're going to be talking about two different shapes and their dimensions. That's when the chart really comes into play. So we're also going to use a chart to organize data. Not only is the chart going to organize data, it's also going to give us information that we're going to use to actually write our equations. Okay? Let's start with our first problem. Now, of the three, this one is the longest. And again, don't skimp writing anything down because this is a model of the type of problem you're going to see on your homework tonight. So the first example, oops, let's go back to black. We've got the length of a page of a book. The length of a page of a book is 2 centimeters greater than the width of the page. So the length of a page of a book is 2 centimeters greater than the width of the page. A book designer, bless you, finds that if the length is increased by 2 centimeters, and the width is increased by 1 centimeter, the area of the page is increased by 19 squared centimeters. What are the dimensions of the original page? So from the top, the length of a page of a book is 2 centimeters greater than the width of the page. A book designer finds that if the length is increased by 2 centimeters and the width is increased by 1 centimeter, the area of the page is increased by 19 square centimeters. What are the dimensions of the original page? So we're going to start by drawing a picture. So we'll start with the original page. And because they talked about area at one point, I'm going to use my equation in this, and I'm going to kind of simultaneously work on my chart. So on my chart, I'm going to have original page, and I'm going to have length, width, area. So we're going to take that area formula and put the area of the product at the end. Amy, you have a question?
Oh, no, sorry.
Okay. All right, so how do I define my length and my width according to this? So again, the first sentence says the length of a page of a book is 2 centimeters greater than the width of the page. So how am I going to write information in my chart or even on my picture to describe what's here? Izzy?
2 plus W.
Okay, so what does 2 plus W equal?
The length.
Okay, so, and I'm going to switch it around because I'm adding 2 to the width. So this would be W plus 2 would be that length, which makes the width the W. So I'm going to put that in here. And the area is their product. So we have a monomial times a binomial. And I don't multiply it out. I can do that later in my equation. But then the book designer comes along and creates a new page. So I'm going to just call it that, new page. And what they say that they're going to do is they want to increase the length of the book by 2 centimeters. Okay? So if the length of the original book was the W plus 2, and then I'm going to increase it by 2, what I get for my new length for the new page is W plus 4. Armand.
Oh, I was just going to say that.
Okay.
I thought you were going to
Nope, not yet. Then they asked me to increase the width, original width, by 1 centimeter. Okay, so I'm taking the old width and I'm increasing it by 1. So that's what the new width is. And the area of the new page, so let me kind of color out what that new page would look like.
Oh, wait, so if you increase one, okay.
Okay, so each side gets only increased once. So I increase the length and I increase the width. So now the area of that outer rectangle, so I have an inner rectangle and I have an outer rectangle, the area would be the product of those two dimensions. But then the problem says this: the area of the page is increased by 19 squared centimeters. So what in my diagram is represented by 19 squared centimeters? My chart has no room for it because it's not appropriate in my chart, because my chart just talks about rectangles. Okay? Justin Pratt?
The box where you did the dash lines around.
Okay. So if you notice, if I go beyond my original page up to where my increases took place, I increased the area of that page. That is your 19 squared centimeters. Okay? So if I want to set up an equation, what I do is I look inside. And I have my original rectangle. I have some additional amount. And that takes me to the outer edge of the new page. So when I write my equation, that's exactly what I write. Here's the area of the original plus the area of the increased amount. And that equals the area of the outer page. So we're looking at rectangles to create our equation. And because that extra piece looks like a backwards L, and there's no formula for the area of a backwards L, they told it to us. Okay, so now we just start solving. So we use our ideas from this chapter. W times W is W squared. W times 2 is 2W plus 19. Over here, I get W squared plus W plus 4W plus 4. So I just am using my double distribution. So this gives me W squared plus 2W plus 19 equals W squared plus 5W plus 4. So I want to get my variables on the left, and I'm a little nervous because working with this W squared is something I haven't done, but as soon as I do that, I recognize, whew, off the table, I'm not going to have to worry about him because the W squareds completely cancel out. So then I'm going to say, okay, I'm going to subtract the 5W from both sides. And then I'm going to subtract the 19 from both sides. So at this point, I have negative 3W equals negative 15. And I divide both sides by negative 3, and I get W equals positive 5. So number one, I have to have positives, because I can't have a dimension that's negative. That doesn't make sense. So what does W represent in our chart?
The width of the larger.
The width of the
Small.
original. W by itself, right here, is right there. For the new page, it was W plus 1, okay? So what I just did was figure out half of my answer. And we would say the width is 5 centimeters. And the length is, and then this is when I plug it into the formula. So I have W plus 2, so 5 plus 2 equals 7 centimeters. And again, this is reflecting the original page, because that's what the question said, what are the dimensions of the original page? So the width is 5 centimeters and the length is 7 centimeters. Okay? All right, so the next problem, another stereotypical. It says a rectangular picture is 2 centimeters longer then it is wide. It is mounted in a frame. Three inches wide. Oh, sorry, 3 centimeters wide. The area of the frame is 168 squared centimeters. Find the dimensions of the picture. Of the picture. So can you think of how we might come up with 2 rectangles in this problem? What would be the first rectangle? Chloe?
The picture.
Yeah, they tell you it's a rectangular picture. Okay, what would be the second rectangle that we would be using in this one? Emily L?
The frame.
Yeah, the frame itself. Okay. So here's something that I'm noticing that you guys seem to be struggling with word problems in particular, is that you guys don't take a whole lot of time to actually observe around you. You kind of just globally take things in, but you don't look at specifics. So what I want to do is share with you a picture in a frame of Tiana. And this is her wearing her, one of her Halloween costumes I've made her. And so it's a rectangular picture, and it's inside a frame. What can you tell me about the frame, other than it's pink, because that's not interesting? Okay. Well, it is for her, but... Jason?
It is bigger than the picture inside.
Okay. Yeah, if it wasn't bigger, it wouldn't be framing it, would it? Okay. Larkspur?
It's wood.
Okay. I'm thinking it's wood. I'm not exactly sure, to be honest with you.
It's
Yeah.
a square.
Okay. Not a square. The dimensions are not the same. They would be a square if the length and the width would be the same. Okay. What else? Tyler B? Okay. Okay. Wow. Good. Okay. Josh?
It's not just a rectangle, but say it's expanded 2 centimeters up and the width and the length.
So what does that mean if it's expanded 2 in the width and 2 in the length?
Almost like the dimensions are almost the same.
Okay. Which dimensions are we talking about that would be the same?
Like it didn't change in size. Well, it did. Just it grew.
If something grows, there's change, right? Justin Pratt?
The frame is thicker than the picture.
I'm not sure if I would say it's thicker. If I took this piece and put it to this piece, it would not go all the way across. So you guys have a hard time explaining, but here's the one thing that nobody said. Look at the frame.
It is about 1 centimeter, or 1 inch,
Okay.
almost.
It is the same thickness here at the top as it is on the side, as it is on the bottom, as it is on the other side. And that's pretty much how frames go. Well, you might have thought that, but you actually didn't ever say that. And that's the key to this whole idea of being framed by something, is that frames, generally speaking, have uniform dimension all the way around. So when we start with drawing our picture of our frame, of our picture, actually. So this is the photograph. There's Tiana in her dress. Okay, being happy. Okay. There's our picture. And we have a frame around it. And what this tells us is that the frame is 3 centimeters wide. So that's 3 centimeters on every side. That's what I mean by its uniform thickness. Okay, the frame is a uniform thickness. So when we are doing a chart, we have the picture. Oops, sorry, go back to black. That's the black edge. is the dimensions of the black edge of the picture. But then we have the frame. And when I'm talking about the frame, I'm talking about the outer pink edge. So we're looking at it as an internal rectangle and an external rectangle, okay? So we're going to talk about it as length, width, and those two multiply to give me area. So what did it tell me about the original picture's dimension? It says in the first sentence, the rectangular picture is 2 centimeters longer than it is wide. So where do I get a variable? Where's the variable go in that one? Who gets to be X? Donovan. Okay, yeah, it mentions width second, and it talks about the length in terms of the width. So width has to be our variable. How much longer is the length than the width? The length is 2. So the area of just the picture would be W times the quantity W plus 2. Now here's where it gets strange, is if you notice, if I want to go down the length, the pink edge of the length, I still have that black edge as part of it. In fact, that's this piece right here. But this piece is 3, and this piece is 3. So when I'm putting in my dimensions, I'm adding 3 from the top, and I'm adding 3 from the bottom for a grand total of W plus 8. I'm going to clean that up. That's not too pretty. Now my width still has the original width of the photo, but then there's these additional pieces that are 3 centimeters each. So I have the width, but then I'm adding 3 from the left and 3 from the right. So this picture that we drew is different from the last picture because we only increased the dimensions on a side, whereas this is being surrounded. So this has dimensions of W plus 6. So we have W plus 8 times W plus 6. Then it says that the area of the frame is 168 squared centimeters. So where in my picture would you see this 168 squared centimeters? What are they referring to? Okay, Chloe? Yeah, they're talking about the totally on the picture of Tiana, that pink part. Not just the outer edge, but the whole pink frame itself. That's your 168. So if we work from the inside out, we have the picture area, which is the W plus 2, plus that additional frame area. That's going to equal the outer pink edge rectangle with dimensions of W plus 8 times W plus 6. Jason.
So the 168, is that only the pink frame, or is it
Yep.
plus the picture?
Nope.
Okay.
Because it says the area of the frame. It doesn't mention the picture at all. Okay. So now I'm just going to be distributing, and when I'm at the level I'm at with my distribution, and I do my outer inner, I do 6W plus 8W is 14W. So I kind of do that step together. And 8 times 6 is 48. Then I'm going to subtract W squared, and again, blissfully, the W squareds cancel out. Next chapter, that's not going to happen. So then I'm going to subtract 14W from both sides, and I'm going to subtract the 168 from both sides. So we get negative 12W equals negative 120, and then I divide both sides by negative 12. And I get W equals positive 10. So the question says, what are the dimensions of the picture? Well, 10 is the width of my picture. To figure out the length of my picture, I'm going to take this value and plug it into the length definition of the picture. So I'm going to have 10 plus 2 equals 12. So my solution is the length of the picture is 12 centimeters, and its width is 10 centimeters. It doesn't matter which answer you list first. It does matter that you get both of them and then you get them labeled with their dimensions. And I had one more problem, but you know what? It's almost identical to this one, but instead of a picture, it's a pool, and instead of a frame, it's a walk. Okay? So our two types of problems really basically are either something increasing just on the dimensions or something being surrounded. So you have a model for the two major types of problems that you're going to be doing on homework.